This is a walkthrough of Problem 1 on Exam 2 in Module 2, which is on page 50 in the book Problem Solving Guide for Electromagnetism and Optics. Problem 1 is a long aluminum rod has a diameter of 1 centimeter and a net linear charge density of -3 nanocoulombs every meter. What is the electric field at a distance of 1 millimeter from the central axis of the rod? That is inside the rod, 1 millimeter only. What is the electric field at a distance of 5 centimeters away from the central axis of the rod? That is definitely outside the rod. So, we need a good diagram. We have a drawing of the aluminum rod. Let's look down the end, on the circular end. And let's make it big so we can see what's going on. The question asks for the field 1 millimeter away from the central axis of the rod, which is right here. The whole rod has a 10 millimeter diameter. We want to know 1 millimeter away from the central axis. If we're going to use Gauss's law, we have to find the charge, because Gauss's law has E dot A is 4 pi k Q enclosed. If we're going to get Q enclosed, we have to know where the charge is. The rod has a negative charge. Like charges repel each other. The negative charges want to get as far away from each other as possible. And because it's a conductor, they're free to move. And they go. They run away. To get as far away from the rest of the negative charge as possible, it's all on the surface. And we can say it's all on the curved surface because it's a long rod. So imagine this rod 1 centimeter in diameter, 2 meters long. If it's 2 meters long, it has a net charge of -6 nanocoulombs. And the ends are a very small fraction of the total area. Most of the area is on the curved surface, so most of the charge is going to be on the curved surface. So let's put it on the curved surface. There it is. Uniformly distributed, as far away from each other as possible. Now we can think about a good Gaussian surface. We're going to get the field 1 millimeter away from the central axis. So let's put it 1 millimeter away from the central axis, and matching the geometry, we make a cylindrical tube. There it is. Here it is inside our other figure. Gauss's law for E dot A is 4 pi k Q enclosed. What's Q enclosed by this surface? Did you say 0? If you did, you are correct. It's all on the outside. There's no charge in here. Q enclosed is 0. E dot A is 4 pi k Q enclosed. We plug in 0 for Q enclosed. That kills the whole right-hand side. The whole right-hand side is 0, which means E dot A is 0. A ain't 0. A is the area of the surface. It has area. The only way this equation can be true is if the field is 0. So there's no field in here. There can't be. The electric field, a distance of 1 millimeter away from the central axis of the rod, is 0. Now, you can answer this problem right away if you understand that there can't be an electric field inside of a conductor at equilibrium when no current's flowing, because an aluminum rod is full of charges. There's electrons all over the place. If there were a field there, the electrons would respond. They would flow. There's electrons right here sitting there. If there were a field there, they would go. There can't be any field there. So you can just state, must be 0. Now part B. What's the electric field a distance of 5 centimeters away from the central axis of the rod, which is up here? 5 centimeters away, outside the rod. We want a good Gaussian surface. Let's make a cylinder to match the geometry of the problem, and let's put the cylinder through the point at which we want the field. So there it is. Nice and symmetric. Now, if you look at this figure, you could certainly imagine some field lines penetrating this disc, the end, because the end of the rod's right here. If I put a positive charge right here, it's not going to be pushed directly outward from the rod. It's going to be pushed a little bit to the right. But the rod's long. So this end is far away from my Gaussian surface. So all of the electric field lines penetrate the curved surface at a right angle. All of the parallel lines are parallel. All of the field lines are parallel to the two circular edges, the top and the bottom of the cylinder, the flat pieces. So no field lines go through the flat pieces. They all go through the curved surfaces, and they all hit the curved surface at a right angle. So E vector dot A vector is E times A for the curved surface. E dot A for the flat surfaces is 0. So here's an end-on view. There's the rod. Here's the Gaussian surface, 5 centimeters away. The field lines look like this. They penetrate the Gaussian surface at a right angle. They hit the rod at a right angle, and they go all the way around. And they're inward because the rod is negative. Now we can consider Gauss's law. E dot A is 4 pi kq enclosed. When we do problems in this chapter, we got one move. There's only one equation. E dot A is 4 pi kq enclosed. Electric field at the surface of the Gaussian surface is the unknown. The area through which the electric field lines are penetrating is the curved surface, and the curved surface has an area of 2 pi r L. Here's the curved surface from a different angle. L is the length. That's this thing down here, the length of the Gaussian surface. The charge inside the Gaussian surface is the part of the rod that's inside our Gaussian surface, our cylinder. The longer L is, the more charge we have. The linear charge density is given, minus 3 nanocoulombs per meter. If we choose a length of Gaussian cylinder of 2 meters, we have minus 6 nanocoulombs inside of it. If we choose 10 centimeters, we have 0.3 nanocoulombs. Let's leave Q enclosed as a function of L, like this. The Q enclosed inside our Gaussian surface is minus 3 nanocoulombs every meter times how many meters we have. We're going to plug that into Gauss's law. 3 nanocoulombs per meter times L. There's Gauss's law. We want to know what E is. The area is 2 pi r L, and we're leaving L a variable. 4 pi k, Q enclosed, is what is in the square brackets. 3 nanocoulombs per meter times L. Make sure that the thing that you're substituting in for Q enclosed is a charge. And this is indeed a charge. The L's cancel. They must cancel. It doesn't matter what you choose for your length of the Gaussian surface, you get the same electric field. So we now have this. We can substitute in for R, the radius of the Gaussian cylinder, which is 5 centimeters, 0.05 meters, and K is some constant. We can solve for E. There's the R, 0.05 meters. There's the Q, without the L because we canceled it. And we get 1080 newtons every coulomb. Now we got to put the direction in. It's toward the rod because the rod's negative. So the answer to part B, 5 centimeters away from the central axis of the rod, the field is 1080 newtons per coulomb radially inward. That's problem 1.